In this module on graphing point, slope, and quadratic equations, part of Business 101B, we're going to look at a number of items that will help us understand how we can conceive of a point slope equation, quadratic equations, how we can graph these equations, and we'll also go to the extent of converting a point slope form to an economic form. So let's take a look at this. We're going to do this in 3 separate video modules. First we'll look at Cartesian coordinate space and the point slope form and a table of values and the axis intercepts. The second video we'll take a look at the quadratic form, and finally the third video we'll consider going from a point slope form to the economic form. So let's first go ahead and take a look at these first 4 items, and we'll start with the Cartesian coordinate space. Well, you'll probably recall from your algebra classes that a Cartesian coordinate space is nothing but some positive, positive, negative, negative, positive, negative, and negative, positive space along an x and a y axis. That's all it is. So if we have, say, a positive value for y of 5 and a positive value of x of 5, then we can find the point here. Sometimes that point is referenced by 5 and 5 or y and x. And we then know that that point is in positive, positive space because it was the result of a positive y and a positive x. So that's the Cartesian coordinate space. As we think about applying a point slope equation to that, an equation maybe that looks something like y is equal to 3 1/3 plus 1/3 x, we can then identify how we will plot this curve in this space, and we'll even think about creating a table of values where we have x and y parameterizing our tables. So let's go ahead and take a look at this point slope form. And the point slope form, as you'll recall from algebra, is y is equal to a plus m of x, where a is some constant. So no matter what happens to x, the value of a doesn't change. And m is thought of as a slope or a scalar variable. As m changes, then it affects x and y changes. Well, in this case, we have our point along our constant and our slope. So if we think about this in the Cartesian coordinate space that we've considered, we have y and x, we can suppose that this is going to be a straight line because there is no exponent on x, or y of course. So this is going to give us a straight line. Since we have a positive scalar variable, it's going to be upward sloping, and I'm going to suppose it's going to come through our coordinate space something like this. We'll focus on positive, positive space, but once this line is began, if it's a straight line, even if it stops here, if we truncate it before it goes into negative space, we know it actually continues on. So let's take a look at this and think about how we might create a table of values that would help us go ahead and plot this line in these spaces. So let's look at a point slope equation that would be y is equal to 3 1/3 plus 1/3 x. When we do that, we have to think of, okay, if we have x and if we have y, we can create some t account, if you will, and we need to give some values of one or the other variable in order to calculate the value of the remaining variable. So I'm going to say, let's go ahead and give values for x, and we'll calculate values for y, because that's what we're doing here. We're calculating y. Y is our calculated or our dependent variable. So I'm going to start with 0. You'll see that it'll start with 0 because here we are at the 0, 0 nexus. So I like that as a starting point and to see where it takes us. So we'll start with 0 and then say go 1, 2, 3, 4, 5, and 6. So if we have this, y equals 3 1/3 plus 1/3 x, So y equals 3 1/3 plus 1/3 times 0. Well, y simply equals 3 1/3. So y equals 3 1/3. And if I then go ahead and say 3 1/3 plus 1/3 times 1, then it equals 3 2/3. Or if I say 3 1/3 plus 1/3 times 2, then I have 4. So I'll just go ahead and fill these values in where x was equal to 1, y was equal to 3 2/3, where x is equal to 2, then y is equal to 4. And I can continue this on, and as it turns out, I can continue it on very quickly because I recognized a pattern develop. You won't always be able to use that because you may not have a consistent change in x. If you have a consistent change in x, you can quickly recognize a pattern that is similarly consistent. But if we'd gone from x of 0 to 1 to 3 to 6 to 12, then we wouldn't be able to have that consistent pattern quite as easily. But we would still have a pattern developing because what we're really saying here is that every time x moves by 1, y moves by 1/3 at a starting point or a constant of 3 1/3. So we see that that has developed here. Well, how do we look at that in terms of our graph? Well, to do that, we actually could simply create our Cartesian coordinate, and I'll do this primarily in positive space with y. In fact, let me change this a little bit. Positive space with y and x. And I said that this is y equals 3 1/3 plus 1/3 of x. And when I had y or x of 1, 2, 3, 4, and 5. And recall that that gave us values of 3 1/3, 3 2/3, and so on. So when x was equal to 1, y was equal to 3 1/3. When x was equal to 5, y was equal to 5. So when x was equal to 5, y is equal to 5. We have a point out here. And having 2 points in a plane and a linear equation, we can now create a straight line connecting them, and that line is known as y equals 3 1/3 plus 1/3 of x. Because as we came along, we simply incremented y by 1, and every time we did it, we incremented x by 1. And every time we did so, we incremented y by 1/3. Well, how do we think about that? We start with this constant, which happens to be the intercept on the y-axis, so y equaling 1/3, y equals our constant. And then beyond the constant, for every 1 unit movement in x, we pick up a 1/3 unit movement in y. We can also think about this as what we'll consider a rise over run. You've seen this before. Rise over run, such that for every 1 unit movement in x, we have a 1/3 movement in y. So we have rise equaling 1/3 and x equaling 1. Or if we want to look at it a little bit differently, make it a little easier on ourselves, if we go from 0 to 3, we have a run of 3 and a rise of 1, or rise over run equaling 1 over 3. Well, those don't give us the axis intercepts, but that just gives us a little bit more definition of this line in some terms that you probably have known for some time. And I know that for most of you this is simply very rudimentary review, but it becomes important as we go further in this course. So now let's think about axis-intercepts. If I look at this equation, I know that if I'm anywhere on the y-axis, I have an x value of 0. And if I'm anywhere on the x-axis, I have a y value of 0. So if I want to find out where this equation lives on the x-axis, I'm going to set y equal to 0. And if I want to know where it lives on the y-axis, I'll set x equal to 0. So let me do that. So if y equals 0, then what I have is 0 is equal to 3 1/3 plus 1/3 of x, or 1/3 of x is equal to negative 3 1/3. I've just rearranged that, of course. I've subtracted 3 1/3 from each side of the equation to arrive at this. Now I'm going to multiply each side of the equation by 3, so I can arrive at x equals 10, or rather negative 10. So I know that out here in negative space, I have negative 10. Well, as I take this further then, if I say if x equals 0, then y is equal to 3 1/3 plus 1/3 times 0, or 3 1/3. So this point was 3 1/3. So if we look at this, this point would have been 3 1/3. So we see the x and the y-axis intercepts, and since again this is a linear equation, we can simply know that it creates a straight line. So this looks at the beginning structure and formation of the Cartesian coordinate space, and here we see how this lines out. Much neater, of course, but I've given you an expanded table of values now. I've gone ahead over here and began with y equaled negative 10, because that is an intercept, and I've taken it through the point where x equaled negative 10. I've taken it to the point of x is equal to 0, and then y is equal to 3 1/3, and then beyond. So I've given us the parameters of our axis intercepts where we see the corresponding values. In the next discussion, we'll take a look at quadratic equations in the next segment in this set of videos for this module.